Mr. Wood, today we're going to go learn about derivatives, one of the most important things arguably in calculus. So let's go ahead and begin. So first off, what is a derivative? Well, a derivative is the instantaneous rate of change of a function. So what we're really looking at here is if we have this graph of y equals x squared right here, if we pick a point, let's say at x equals 2 right here, we want to see just about how that function is changing at this specific point in time. It looks like right here that it's going to be increasing. At the moment, we don't quite know at what rate it could be increasing at that specific point, so that's what we're going to find out. So we have this notation here for our first derivative. We can take derivatives of functions many times, usually. Our first derivative, we could be using this notation, dy over dx, or this one right here. This looks like a little apostrophe here, and we pronounce that as f primes of x. If we do a second derivative, we'll have d squared y over dx squared, or f double primes of x, and we can keep doing that. Like a third derivative will be d cubed y over dx cubed, or f triple primes of x, and we keep going, keep going, keep going. We can evaluate our derivatives at any number. In this case right here we have constant a, so if we wanted to use the dy over dx notation, it would look something like this, with this bar here and an x equals our number, or in this case a. Or if we're using this notation, it'll just be simply f primes of a. Alright, so what is differentiability? So differentiability goes along with derivatives very closely. So if you'll take a look down here, a function f of x is said to be differentiable at x equals a if f primes of a exists. So if we take the derivative and evaluate it at a, and that exists, then we say that that function is differentiable. Similarly, if a function is said to be differentiable on an interval, if the derivative exists for each point on that interval. So if we have an interval, let's say on this graph of y equals x squared, if the interval is from -2 to +2, if we can take the derivative of each and every single point on this interval, then that function is differentiable on that interval. So we also say that if f of x is differentiable at x equals a, then f of x is also continuous at x equals a. So since we can say take the derivative at this point, we know that that function is continuous at that point. So something like this function over here, this funky one, if we wanted to take the derivative at this point, we can't take the derivative here. And so we know that the function is not continuous, which clearly you can see because the graph is going up this way, and then suddenly it jumps down here and does a little upside down parabola sort of deal. So we know that this is not continuous, and therefore it is also not differentiable. So how do we calculate a derivative? Well, we have to remember our limits and how to calculate those, and whatever function we're using, we are going to plug in x plus h for anywhere that there's an x in that function, and then subtract the original function itself and divide by h, and we will be taking the limit as h approaches 0 of all of that jazz. So why don't we just go right in, jump in with an example so we can see how that works. So our first example, we want to find the derivative of f of x, where f of x equals 2x squared minus 16x plus 35. So like I said before in the last slide, we want to take x plus h, plug it into everywhere that we have an x in this function, and then subtract the original function and divide it by h. So that's what we have here. So we have our limit notation. Since we're taking a limit, we'll need that in front. Plug in x plus h to each point of the function where we have x, and then we want to subtract the original function over here. So what that's going to end up doing is changing all of our signs here, and we'll get to that in a minute. So we kind of want to focus over here. We have 2 times x plus h squared minus 16 times x plus h plus 35 minus our original function over h. Moving on. So from here to here, we expanded this x plus h squared. So we did x plus h times x plus h, and we get x squared plus 2xh plus h squared. Here, we distributed our 16 to the x plus h. So we have minus 16x minus 16h plus 35, and then subtracting our original function over here. The next step, we want to distribute this 2 to each of these terms. And I'm sorry, I should have a 2h squared right here. Distribute that 2 to each of these terms. 2x squared plus 4xh plus 2h squared. Carry the minus 16h and minus 16x from up here, plus 35. And then from this step, we distributed this negative sign to our original function. Since we are subtracting the entire thing, we want to distribute the whole negative. Now for the next step. The next step, what we want to do is we want to try to cancel out as many things as we possibly can. So you might have noticed already that we have some of the same terms in this expression right here. So it looks like we have a 2x squared here and a 2x squared here, so we can cancel both of those. We have a negative 16x and a positive 16x, so we can cancel those out. And we have a positive 35 and a negative 35, so we can cancel those. Alright, we have nothing else we can cancel, so let's move on. Now, what you might notice here is that all of our terms that are remaining that haven't been canceled out still have an h in them. And our whole function here is over h. So what we can do with that is we can cancel this h with an h in every term, so the h goes away in 4x. We lose an h for h squared, and the h goes away for negative 16. Alright, now if you follow along here, what we'll be left with is the limit as h approaches 0 of 4x plus h minus 16. If we evaluate this limit as h approaches 0, we plug in 0 for h, so we have 4x plus 0 minus 16, so we know this h can just go away. And we will finally be left with this, our derivative of f of x, which is f primes of x, equals 4x minus 16. Okay, so remember, since we're taking a limit for this entire problem, we need to keep this limit notation in here for every step until we get down to here, where we finally evaluate it and we can take out that h. Alright, so this derivative right here will tell us what is happening with this function at any point that we want to plug in for x. And we will get along to that in a minute as well. But let's continue on with another example. So we want to compute dy over dx of x cubed. So remember, this dy over dx is just a different notation for the derivative. It's pretty similar to f primes of x. This is just telling us to take the derivative of whatever is in the parentheses. So we want to compute dy over dx of x cubed. Alright, so we're going to do the same thing with the last problem. Everywhere there's an x in our function, we want to plug in x plus h, and then we want to subtract the whole function by itself and divide it by h while taking the limit as h approaches 0. Alright, so now what we want to do is we want to expand this x plus h cubed, as well as distribute this negative to x cubed. So we have x plus h times x plus h times x plus h, which is x plus h cubed, minus x cubed. Now we want to expand that further. So if we do x plus h times x plus h, we should end up with x squared plus 2xh plus h squared, because we multiply x plus x for x squared, h plus h times x for an xh, h times h for h squared, x times h for another xh, so we get 2xh. And we still have this x plus h over here, so we'll have to expand that even further. So when we expand that, and you should be able to do this on your own, we should get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed. Alright, so just like this last problem, we have some things that we can cancel out here. We have an x cubed and a negative x cubed, so those can go away. And all we're left with is this. The limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed. And we might need to continue this on the next page because we are running a little short of room. So this is what we were left with on the last page. 3x squared h plus 3xh squared plus h cubed over h. What we want to do now is cancel an h on the top and bottom. So since we're dividing by h, we can get rid of an h here, we can get rid of an h here, and this is going to actually become h squared. Okay, so we have 3x squared plus 3x plus h squared, right? And we are taking the limit of that as h approaches 0. So what we can do is plug in 0 for everywhere that we have an h, which means we have here 3 times x times 0, so that's going to go away, plus h squared or 0 squared, so that's going to go away, and we're going to be left with dy of d over dx equals 3x squared. So that's going to be our derivative of the function y equals x cubed. So finally, if we want to evaluate a derivative at any point, that is going to tell us what is going to happen on our graph at that specific point. So we know from the last problem that if we have the function f of x equals x cubed, that its derivative here is going to be f primes of x equals 3x squared. So if we want to evaluate that derivative and see what our function of x cubed is doing at any of these points, we just need to plug this into our derivative. So if we want to find f primes of 0, we just do 3 times 0 squared, right? So this one's pretty easy. Of course, 0 squared is going to be 0 times 3 equals 0. So on our graph at f of 0, that's going to be right here. What is our function doing? Well, our function is completely flat. So what this is telling us is that we have a slope at this specific point at x equals 0 of 0. So our function isn't increasing, it isn't decreasing. So let's take a look at f primes of -1. So let's plug that in. So we got 3 times -1 squared. -1 squared is going to be +1 times 3 is 3. So let's see, let's erase a little bit of this. If we have to look at -1 for f of x, that's going to be here, right? Well, it looks like at x equals -1, our function is increasing. And we can actually say that if we were to have a line here, that the slope of that line is going to be +3. So this is really what our derivatives are telling us about our function, is how our function is going to be increasing or decreasing. So let's try one more thing at f primes of 3. So let's plug that in. We have 3 times 3 squared. Well, 3 squared is going to be 9. 9 times 3 is 27. If we're looking at f of x equals x cubed, that x equals 3, that's 1, 2, 3. Well, our line, our function is kind of doing something like this at that specific point. So at this point where x equals 3 on our graph, it is increasing instantaneously at a rate of 27. So that's what I said up here, where it is our instantaneous rate of change of a function. At this moment, our function is going up at a rate of 27. All right? So that's our introduction to derivatives for today. Hopefully you will be familiar with this for tomorrow, for when we start to explore derivatives a little bit more. I hope you have a great day and see you in class.